Picture this. You're going about your normal day when suddenly every news channel breaks with the same terrifying headline. A massive asteroid, bigger than Mount Everest, is hurtling toward Earth at unimaginable speeds. Scientists have calculated the impact will create an explosion equivalent to billions of nuclear bombs, triggering mass extinctions and potentially ending human civilization as we know it. The question isn't whether this could happen, it's when.
And more importantly, are we prepared to fight back?
Today, we're diving deep into one of humanity's greatest existential threats and exploring whether our species has what it takes to prevent our own cosmic extinction.
The answers might surprise you, and some of them are absolutely terrifying.
Right now, there are over 30,000 known asteroids larger than 140 meters crossing Earth's orbit. That's just the ones we've spotted. Astronomers estimate there could be hundreds of thousands more lurking in the darkness of space, invisible until they're close enough to spell disaster. Every single day, our planet is bombarded by cosmic debris, most of it burning up harmlessly in our atmosphere. But history shows us that the big ones do get through, and when they do, the consequences are catastrophic. 66 million years ago, an asteroid roughly 10 kilometers wide slammed into what is now Mexico's Yucatan Peninsula. The impact created a crater over 150 kilometers across and triggered the mass extinction event that wiped out the dinosaurs. The explosion was millions of times more powerful than the largest nuclear weapon ever detonated. Imagine that same scenario playing out today with our interconnected global civilization, our cities packed with millions of people, our delicate infrastructure that keeps modern life functioning. But here's what makes this threat even more chilling. Unlike earthquakes, hurricanes, or volcanic eruptions, asteroid impacts are completely unpredictable in human terms. We might get years of warning, or we might get just weeks. In some cases, asteroids have been detected only days before they would have hit us. The margin for error is razor thin, and the stakes couldn't be higher. So what exactly would happen if a planet-killer asteroid was discovered heading our way? The immediate response would involve every space agency on Earth working around the clock to calculate the precise trajectory, impact location, and timeline. This information would determine everything about our response strategy. The harsh reality is that different asteroids require completely different approaches, and some of our most intuitive solutions simply don't work the way Hollywood has led us to believe. Let's start with the most obvious idea that comes to mind when people think about stopping asteroids: nuclear weapons. It sounds straightforward enough, right? Launch a missile, detonate a nuclear warhead, and blow the asteroid to pieces. Unfortunately, the physics of space makes this approach far more complicated and often completely ineffective. The first major problem is that most asteroids aren't solid chunks of rock and metal like we tend to imagine. Many of them are what scientists call rubble piles, essentially loose collections of rocks, dust, and debris held together by weak gravitational forces. Hitting one of these with a nuclear weapon would be like trying to destroy a pile of gravel by throwing a firecracker at it. The explosion might scatter some material around, but the bulk of the asteroid would continue on its deadly trajectory, potentially creating multiple smaller impacts instead of preventing the collision entirely. Even if we're dealing with a solid asteroid, detonating a nuclear weapon on or near its surface faces another fundamental challenge. There's no atmosphere in space. Nuclear explosions derive much of their destructive power from the shockwave that travels through air. In the vacuum of space, you're left primarily with radiation and thermal energy, which are far less effective at physically displacing a massive object traveling at cosmic speeds. This brings us to some of the more sophisticated deflection methods that scientists and engineers have seriously proposed. One approach involves using the gravitational pull of a spacecraft to slowly tug an asteroid off course. Called a gravity tractor, this method would position a heavy spacecraft near the asteroid and use the tiny gravitational attraction between them to gradually alter the asteroid's path. The key word here is gradually. This technique requires years or even decades to produce meaningful course corrections. making it useless for last-minute discoveries. Another strategy involves physically impacting the asteroid with spacecraft to change its momentum. This is actually the approach NASA tested with their recent DART mission, which successfully altered the orbit of a small asteroid by crashing a probe into it at high speed. The results were promising, but again, this method works best when you have plenty of time to plan and execute multiple missions if necessary. Solar radiation pressure offers another intriguing possibility. By deploying massive mirrors or solar sails near an asteroid, we could theoretically use sunlight itself to push the object off course. Some proposals suggest painting one side of an asteroid with reflective material to create an imbalance in how it absorbs and reflects solar radiation. Over time, this could produce enough force to deflect its trajectory. But like other gentle deflection methods, this requires enormous lead time that we might not have. For scenarios where we have very little warning time, scientists have proposed more dramatic interventions. One concept involves using multiple nuclear devices not to destroy the asteroid, but to vaporize material from its surface. This would create a jet of high-velocity gas that could act like a rocket engine, pushing the asteroid in the opposite direction. The challenge is calculating exactly how much force this would generate and ensuring the asteroid doesn't just break apart into multiple dangerous pieces. But what if we're dealing with the ultimate nightmare scenario? A truly massive asteroid, something in the 10 to 20 kilometer range that could trigger a global extinction event? These cosmic mountains present challenges that push our current technology to its absolute limits. The amount of energy required to meaningfully deflect such objects is staggering, potentially requiring dozens of the most powerful rockets humanity has ever built, all launching in perfect coordination. Here's where the discussion gets really interesting, because it forces us to confront some uncomfortable truths about our current capabilities. As of today, humanity has exactly 2 spacecraft specifically designed for asteroid deflection missions: NASA's DART probe, which has already completed its mission, and the European Space Agency's HERA probe, which is still in development. That's it. Our entire planetary defense fleet consists of experimental missions that weren't even primarily designed to save the world. The timescales involved in mounting a meaningful defense are equally sobering. Current estimates suggest that deflecting a large asteroid would require at least 5 to 10 years of preparation, assuming we had the necessary technology ready to deploy. For the biggest threats, we might need decades, yet astronomical surveys regularly discover asteroids that would impact Earth in just months or years. The math simply doesn't add up in our favor. This leads to what might be the most crucial realization in this entire discussion. The asteroid deflection problem isn't really about the technology, it's about detection and preparation time. Every month of additional warning time exponentially increases our chances of successfully mounting a defense. This is why astronomical surveys and space monitoring systems are arguably more important than any exotic deflection technology. Organizations like NASA's Planetary Defense Coordination Office and the European Space Agency's Space Situational Awareness Program are working around the clock to catalogue potentially hazardous asteroids. Their goal is to identify threats decades in advance, giving humanity enough time to develop and deploy appropriate countermeasures. But these efforts are dramatically underfunded compared to the scale of the threat they're trying to address. Consider this. The entire global budget for asteroid detection and planetary defense is less than what some countries spend on their military forces in a single day. We're essentially gambling the future of human civilization on a budget that wouldn't fund a major infrastructure project in most developed nations. The disconnect between the magnitude of the threat and the resources dedicated to addressing it is staggering. But let's assume for a moment that we detect a planet-killer asteroid with sufficient advance warning and decide to mount a serious deflection effort. What would that actually look like? The most realistic scenario would probably involve a coordinated international response combining multiple deflection techniques. We might begin with gentle methods like gravity tractors or solar radiation pressure to start nudging the asteroid off course. As the impact date approaches, we could escalate to kinetic impactors, essentially space bullets designed to transfer momentum to the asteroid through high-speed collisions. If those approaches prove insufficient, the final option might involve nuclear devices, but used in a much more sophisticated way than simply trying to blow the asteroid apart. The goal would be to vaporize material from the asteroid's surface in a controlled manner, creating thrust that pushes it away from Earth. This would require incredibly precise calculations about the asteroid's composition, rotation, and structural integrity. The engineering challenges involved in such a mission are mind-boggling. We're talking about coordinating launches from multiple countries, managing spacecraft across millions of kilometers of space, and executing precision maneuvers with objects traveling at speeds of tens of thousands of kilometers per hour. The margin for error would be essentially zero, because there are no second chances when dealing with extinction-level threats. Even if we successfully deflect the asteroid, we'd face entirely new challenges. Moving a massive object through space creates ripple effects that can alter the trajectories of other asteroids and space debris. We might solve one problem only to create several new ones down the line. This is why some scientists argue that breaking up large asteroids might actually be preferable in certain situations, despite the risks of creating multiple smaller impacts. The psychological and social dimensions of an asteroid threat are equally complex. How do you maintain social order and international cooperation when facing potential extinction? How do you fund and organize a multi-decade defense project when political leadership changes every few years? These aren't just technical problems, they're fundamental challenges about how human societies respond to existential threats. Recent advances in space technology do offer some reasons for optimism. Private space companies have dramatically reduced launch costs and increased our ability to deploy large payloads into space. Advances in artificial intelligence and autonomous systems could enable more sophisticated asteroid deflection missions that don't require constant human oversight across vast distances. New propulsion technologies like ion drives and solar sails are making long-duration space missions more feasible. Perhaps most importantly, the scientific community's understanding of asteroids has improved enormously over the past few decades. We now know that most asteroids are far more fragile and loosely bound than previously thought. This knowledge could be leveraged to develop more effective deflection strategies that work with the asteroid's natural structure rather than against it. Looking toward the future, some of the most promising asteroid defense concepts involve permanent space-based infrastructure. Imagine networks of automated spacecraft stationed throughout the solar system, constantly monitoring for threats and capable of immediate response. Such systems could detect and deflect smaller asteroids before they become problems, while buying precious time for humanity to respond to larger threats. The bottom line is this: humanity absolutely can develop the capability to stop planet-killing asteroids, but only if we treat this threat with the seriousness it deserves. We need sustained international cooperation, massive increases in funding for detection and deflection research, and a commitment to developing these capabilities before we desperately need them. The physics of asteroid deflection are well understood, the engineering challenges are solvable, and the technology is within our reach. But we're running out of time to prepare. Every day we delay building robust planetary defense systems is another day we're gambling with the future of our species. The dinosaurs didn't have a choice when their asteroid arrived. We do, but only if we act now while we still can.